Hi everybody, it's Dr. Chabot, and in this video we're going to talk about what happens when we put multiple resistors in a circuit. So just like with capacitors, we have these two ways of combining them that we're going to be able to analyze, which is going to be series or parallel. So let's go ahead and start with a series combination of resistors. So in this case, I would have a resistor, say R1, in series with R2, and then they are in series with some power supply, delta V. And again, the series configuration is that one loop then passes through both resistors. So if we remember that for the resistors, right, it's like the number of collisions increases the resistance, right? So we would have, more collisions equals more resistance. And that the collisions and the resistance are going to be what are taking and converting our electric potential energy to thermal energy. Right? So essentially, as the electrons, remember our electron guys, carrying their buckets, and their buckets have their energy in them, then as they're colliding, that energy is spilling out and turning into thermal energy. And so if we put two resistors in a row, right, then we're going to have some amount of collisions with my current. Again, the current kind of just is just dq dt. I have to have the same current through both, right? So I would have to have I1, and then here's the I total, and I2. We can see that the total current of the battery is going to have to be equal to the current through R1, which is just I1, which is also equal to the current through I2, right? So that comes from just this idea of conservation of charge. Because remember that current is just dq dt, right? It's charge per time. So that there's just no one place in this circuit that is accumulating charge, right? We have a charge separation at the battery, but the current flow is uniform throughout one loop. So all parts of the loop have the same current. And so that's going to be one result that we need to use in order to analyze the situation. We can also see that when we have these multiple resistors in series with each other, that we get some amount of collisions from R1. And then if that same current, those same electrons with their buckets have to go through R2, then that's even more collisions. So the series combination is going to make more total collisions. And so that's going to be a higher total resistance. So like if we're trying to get the electrons through, and then they have to go through both things, then you're going to have that higher total resistance. And we also we want to remember our Ohm's law, which is really, again, just the definition of resistance, which is that delta V equals IR. And so we can then say that this is going to be true for the total, right? For the total battery. And so the total current, and then whatever we're going to call some equivalent resistance of the circuit. But it's also true for some individual resistor, where the voltage drop across that resistor will be equal to the current through that resistor times its resistance. So for example, R2 would have a delta V2 across it like so. So that would be its voltage drop from one side to the other. So if we go ahead and kind of combine these ideas, we can find our total equivalent resistance. So let's find the total, quote, equivalent resistance, and that would again be as if what could we have here instead of these two resistors, what could the power supply see in place of those two resistors? So we can start with this equation. We can see that we would have that Req is going to be equal to delta V total over I total. And our delta V's, because again, it's just how it worked before, that we're going to have the voltages adding. So delta V total is going to be equal to the voltage drop across 1 plus the voltage drop across 2. And then I total is going to be down here. And I total does equal I1, which equals I2. So I could write this as delta V1 over I1, since that equals I total. And so I'm just choosing in that instance to write it in terms of I1 because it matches the voltage drop across the top, and then plus delta V2 over I2 because that also equals I total. And so then I can see that my equivalent resistance for series is simply going to be delta V1 over I1 is just equal to my resistance R1 plus my resistance R2. So it's a pretty obvious result that if I put them in series with each other for resistors, I have more and more collisions, and my total resistance is simply going to be equal to the sum of all the individual resistors. So that's a key result for us for our equivalent resistance in series. I do want to take a step back and I want to talk a little bit more and just reinforce this step with our voltage, because we'll see that voltage acts the same now as it did with capacitors. So I'll say here, note that voltage acts the same now as with our capacitors. And that's because voltage just is what voltage is, which is these hills that are getting created. So if we start with this picture again, remember that I have some positive voltage here at the power supply. That's equal to my total hill. So that's my positive voltage. And then I have my negative voltage at the bottom. And this entire side all has that V positive, right? That entire line is all at positive V. And on the very right-hand side, that negative line is all at the valley, at the negative V. And then this is some voltage in between, right? So that's an in-between voltage. And so if we look at the voltage drop, say, across the first resistor and the voltage drop across the second resistor, right, then what we end up with is essentially the first resistor here is going to be starting at plus V, and then it has some voltage drop. That goes to our middle value, and then this value here is my delta V1, and then it goes through the next value, that's my delta V2, and then I come back down to V minus. And so I have all of the same total energy loss that we had started with in this situation, and it just gets divided up between them. So noting that in series, again, we have that the current is going to be equal, and the voltages add. And that's again in series. So I'm going to box that as well, and we have our analysis of the series circuit. So now let's go ahead and talk about what happens if it's in parallel. So if we have parallel, we have a resistor, and then in a separate branch, we have another resistor. So we'll call that R1, and R2, and then we have the voltage of the power supply. Now, again, let's just talk about voltage first, since that's what we've been talking about. So we'd have this positive voltage, this entire part of the wire, there's nothing in the way, is all going to be at plus V. And then on the right-hand side, this entire side is going to have these wires all at minus V. And so we can see that each, just like with capacitors, the voltage in parallel is going to be the same for all. So the voltage is the same in parallel. And it's going to be the currents that add. We'll see that in a second. So the voltages are the same. That means that delta V total equals delta V1 equals delta V2. And then in terms of the currents, the current is going to split at the junction. Right? So now we are picturing our charge carriers coming around. We have our current. And if we just again imagine our positive charge carriers, then some of them have to go through R1 and some go through R2, right? So they pick R1 or R2, and the electron guys can't go through both, right? They're holding their buckets. They have their energy. They're going to dump all their energy out into just whatever one they pass through. And so we can say here then that the I total is going to then have to be equal to I1 plus I2 in parallel. And so in parallel, the currents add. Again, just like how the charges had a split for capacitors at the junction, here it's the same idea. Remember, current is charge per time. And so we can use these then to talk about equivalent resistance of this circuit, which would be, again, what could we call essentially the total resistance of this circuit that the battery sees. And so we can say delta V total equals I total times REQ, and REQ then can be written as delta V total over I total, and so this ends up just being delta V1, right? Delta V total is delta V1 is delta V2, and so this is just then delta V, I'll call it delta V total still, over I1 plus I2. When we go through the algebra of solving this for REQ, we get this inverse relationship, 1 over REQ equals 1 over R1 plus 1 over R2 plus however many parallel branches there are. So we have this result for our resistors in parallel with each other. Notice that these results for the equivalent value, the equivalent capacitance or the equivalent resistance, are switched relative to each other. But for the voltages, voltage just is what it is. It doesn't switch. That rule doesn't switch. It works the same whether it's resistors or capacitors, and charges and charge per time. That just does what it does. It doesn't vary depending on what is happening, what you put in a capacitor or a resistor. So it's just these equivalent values that switch for our series or our parallel configurations. And this one makes sense because now, right, we're gonna, if we think about why that would make sense, is that when we have a junction and we can split our current, I1 and I2, and then I total, then you're gonna actually have less total collisions, right? When in parallel. And so we're going to then be able to have a lower REQ. By giving kind of multiple pathways for the electrons to go through, then there's less total collisions as you've given them more kind of hallways to walk through. Okay, I hope that this helps introduce the idea of how resistors behave in circuits when there's multiple versions of them.